So we're going to go to D2L, go to content, and of course, this is going to vary depending on term and course. But we're going to go to the location where currently resides the sample distribution of the main material. And here I have a particular course, and we're going to do is download this guinea pig data. So I'm going to come over here and just download it, and I'll go somewhere, and I'm going to open it up and go back. And then the next thing I'm going to do is I'm going to click on the Rossman-Chance Simulator right here. And I'm going to go under Sampling Distribution Simulations, which is this title right here. And I'm going to choose on Sampling Words. And what am I looking here? Well, you're looking at a histogram showing the length of words used in the Gettysburg Address by Abraham Lincoln. And you can see the histogram. You can notice if you look at the words here, 7 years ago, our fathers brought, and now what we're measuring is the length of the words. 4 is 4, score is 5, and is 3 letters, 7 is 5 letters, and so on. But we're looking at the length of each word for the Gettysburg Address, and we'll notice that the mean number of letters is 4.295. But let's look at these questions. What is the shape of this distribution? So when I'm looking here, I'm clearly saying that this is skewed right. Okay, so I'm going to click change population to times 100. So I'm going to do that. So right now it's times 1. You notice the population is 268. There's 268 words and the Gettysburg Address. So I'm going to just multiply that by 100. So I'm going to do that. So now what is the population size? 26,800 words. And of course, what we're measuring is the length of the words. So the unit is length of words. So I'm going to let the random variable L measure the length of a word. What is E of L? Using this notation, this is the population mean. So right now, when I look at this histogram, I'm assuming this is my population. As a matter of fact, look at the title. It says population data. So we're saying this is the Gettysburg Address. That's all we care about. The population size is 26,800. So imagine that we took Gettysburg Address, created 100 versions of these things that are the same ones, and then we cut up all the words and throw them inside a basket. So the mean of this distribution I can see is 4.295 words. And the standard deviation is going to be 2.119 words. Word, I guess not words. I should say length of words. So this is open at letters. So we're just counting the number of letters in each word. Again, there's my mean, there's my standard deviation, there's my population size. This is the population we're sampling from now. So now what are we going to do? We're going to sample words with replacement, meaning if I sample the word 4, I can resample it again. Every time I sample a word, I'm going to replace it, put it back in the population. So I can grab exactly the same word that I've already sampled. So meaning after we sample a word, calculate the word length, it gets put back in the population before we sample again. That's what with replacement means. Think of it like tossing a die. The population makeup is not changed. Question mark? No. Exclamation. It's not changed. So now I'm going to check the box label sampling options. We're going to do that. Great. Now what? Change the sample size to 5. So over here, number of samples, 5. Notice it does have you stratify samples by, cluster samples by. Interesting. But we're not going to choose either of them. If we did that, we're now going to click on the Draw Sample button, which will simulate sampling 5 times and calculate the sample mean. So I'm going to go Draw Samples. No, number of samples is 1. Sorry, sample size. I'm going to put in 5. That should read. That's a sample size. And I'm going to just do this once for a moment, just to get the idea. Number of samples is 1. The sample size is 5. Draw the sample. And there we go. You can see what words were chosen. And notice that the ID, so the 7,380th word was chosen, which was note, which was 4. Nation was another word chosen, which was at position 19,921. R was at position 15,172, and so on. Okay, so these are the words chosen. These are the length of each word, and you can see that right here. These are the different lengths of the words. And my sample size was 5, and what do we get? So in this case, the mean was 4 for my first one. Yours is going to be different. That was nice and convenient. So what's happening is we sample these words, take these, add them up, divide by 5, and you'll see that the mean is a 4. I'm going to do this 15 times, and each time I'm going to draw and place the sample mean. So this is, can't emphasize, but this is a sample mean. So let's do this again and enjoy the experience, please. 5.6 is the next sample average from these words that were chosen randomly. I got a 7, a 5, 5, 8, and a 3, but the average is 5.6. Let's try again. And each time I'm going to down the mean. And we're going to do this 6 times. So really what I'm after here is get an understanding of what happens when I sample 5 words at random and get a sample mean. So notice the first one was 4. Notice it was also very close to the sample, the population mean. Do it again. And I'll write this down, another 5.6. So again, I'm reading here, and you can see the location of the samples, the different words, like there was a 4, there's a 10 way out here, a 3, and a 4, and a 4. And that's why these two are stacked up. And you can see the mean, where the mean of these numbers is located. Draw again, 4.2. Draw again, 3.6. And 4.8. And I'm going to do this, and I'm going to pause the video in a second because you don't need to see me doing this every single time. So again, clicking, reading here, look at the words just for fun, 3.8. You could also stare at this graph and see the length of the words that made up those 5 individuals. These are 5 individual numbers. And if you look here to the left, you actually see where they're located. 6. Again, I know that 6 is extreme, so it must have had some, sure enough. Looks, it has a couple low values, but also had 3 or higher values. And I got a 7, a 9, and another 9. 2 9s all of a sudden. Notice a 9 is very unlikely, but it does happen once in a while. And now these are my 15 numbers. What does this mean? Each one of these is an approximation. So write the approximation symbol to what? E of L, which in this case happens to be 4.295. So if we sampled 5 numbers and somebody asks, well, what is the average length of the words in the Gettysburg Address? You can say 4. But if you sampled this one and that was your result, I would say, well, my estimate, these are all estimates, these are approximations, is 5.6. If you sample this one, you say, well, the average length of the words is 6.2. If you sample this one, this was your single value, is 5.6. When you sample, you only sample once. But now we're going to see what could have happened if you sample different times. Okay, so this is what happens. And you can notice there is a bit of variability, but there's also some repetition. 3.6, notice this 3.8, 3.8, and notice 3.6 is pretty close to 4. The 4.8 is a little more extreme, 3.8, getting close, 3.8. 6, but there's a lot of variability here. A 4, that's really nice and close. 4.2, nice and close. So sometimes you get numbers that are pretty close, and then after a while you start getting numbers that are far away, but they don't happen too often. So I'm going to say that 6.2 was definitely far away, so it was a 6. And then you have this mid sort of somewhere in there. You know, maybe I'll call this another mid, There's happening though. I'm going to make that, call this mids too. So there's some close and some mids, and then some that are far away. But again, each sample is only 5 words, but each one is an approximation for that. Now change the number of samples to 9,000. This will do 9,000 iterations and generate 9,000 additional sample means. The left graph will show the last sample taken, select draw sample. So now I'm going to go the number of samples. Number of samples is going to get to 9,000. So by the time I hit draw, what will happen is I will have 9,015 sample means of size 5. So I'm going to do that. Right here, what I have is the last mean from the last is the most recent sample was 3.6, which is in line with what happened here. You see where they came from. Now, what I want you to see now is the sampling distribution of the mean. And this one, I should have done it earlier, but I didn't. Maybe I'll do this again. This is now the sample statistics. This represents the means from this case, the 9,015 samples that we just drew. And now you start to look at the shape of this thing. So I'm going to go reset really quick so you can see it. So originally I just did 1. So I'm going to go 1, 2, 3. You can see things are stacking up. This is now the distribution of these sample means. Drop, 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 drop. You can see where they're landing as I'm doing this. How many times have I done this now? 13, 14, 15. So there's another 15 I drew, and these are, each one is marking the sample mean. Notice the last one was 3.2, and that's, you see, there it is in blue, and marks the last one, 3.2. These are the individual values that make up this mean, and then we take this mean and place it in the sampling distribution. But of course, if I keep doing this, you start seeing the different possibilities and the likelihood of the possibilities. So I'm just clicking really fast. I'm up 75, 78. And each time, so what I'm doing is, what are other possible means, and how likely are these means to occur? So I'm going to come back here. How many did I do yet? 111. So I'm going to go, I want 9,000. So I'm going to go 8,900. Draw samples. And you could just keep doing it yourself. Boom. And now I got 9,011. So I'm going to go, what is the shape of the sampling distribution for when the sample mean is 5? So now this is 5 for n equals 5. So this is very important. Sample size here matters. 9,000 is not the sample size. The sample size is this right here. Each individual mean is what we're looking at. So right now n is equal to 5. So, and in my thing, I iterated the process 9,000 times. So what we're speaking of right now has nothing to do with this 9,000 number. That's a number of iterations. It has to do with each little individual. So when we say, what's the sampling size? It's sample that makes up a summary. Makes up, oh, we should have more room here. This is like a puzzle here. Summary. Oh man, this is what I don't like to do. Sample that makes up summary, that's what we're talking. We say sample 5. So what is the mean? So I look over here and I see that it's 4.31. What is the standard deviation? 0.95. And what do you notice? Well, one thing I notice is, hey, 4.3 is very close to this number. Okay, and we're going to see what should be the relationship. Now, this is still, no matter what, a summary. This is not a parameter, but this is, notice, the symbol for a parameter. I do have equal signs here because I'm trying to say, look, these are supposed to be the parameter, but it's really still, because I only iterated this 9,000 times, this is still a sample, but the symbol is of a parameter. This is a parameter because I know exactly the number of words there were. It was 26,100, so this is definitely a parameter. That's not a sample, because I define the population to be those 26,800 words. But here I've only iterated 9,000 times. So no matter what, how big is the population of means? The reality is it's infinite, because I can keep sampling forever like this. But even though it's forever, there's still a true mean. And just like this one, there's also a true standard deviation. This is a very good approximation of the standard deviation of the sampling distribution of the mean for a sample size of 5. And again, notice 0.95, it's about 1. So I'm noticing here that, look at the mean is 4.3, somewhere here, and then the average distance is about 0.95 away from that mean. So you can see here, I have my guinea pig data that I mentioned we needed. And where did that come from? I come back to this week 4. And remember I said, go ahead and download this. And then once you download it somewhere on your computer, open it up. And when it opens up, it looks like this. So now I'm going back to the Rossman-Chance Simulator. And what I'm going to do, see this clear button? We're staying here with the Rossman-Chance, but I'm going to hit the clear button. Just wipe this all out. Clear. Great. Now what I'm going to do, paste the data using the data button. So I'm going to come over here and I'm going to highlight. I think I'm doing the right thing. Click on here. I can't remember if this is how you do it. I'm going to find out in a second. Come back here and right click, and I'm going to paste. And that was the right thing to do. Okay, and I have my days. Great. I'm going to say, tell the computer to use data. Perfect. Notice the days is a title. I didn't need that. It has the ID. It has here, each number is now getting a little ID, so we can see what the distribution is like. And I can see, notice that this is a little different. So, 1 second, I'm going to get back to my, now that I have this, I don't no longer need the Excel file. So now that I'm back here, let's answer some of these questions. What is population size? I have my population size is 7,200 days. What is the shape of the distribution? And it's right skewed, but definitely compared to the Gettysburg address, this is more skewed than the last. Would you call it severe? Yeah, like maybe the other one that was said was skewed right. I'm going to call this moderate. This is more, I don't know, not severe, but I don't know, definitely more than just moderate. So maybe if you call that one moderate, I would call this one right skew for sure. All right. What is now the mean of this population? So the population consists of the number of days. It looks like the mean number of days the guinea pigs survived was 137. And these are days, is the unit. What is the standard deviation? Well, again, looking at that output is 96.251. And again, the unit here is days. That's one standard deviation. So this is my population. So notice population data, mean, standard deviation, population size. Okay, fantastic. Now change the number of 10,000, leave the sample size at 5. Okay, so we're going to now change this number of samples to a clean 10,000. And if you want, again, just to re-emphasize, I'm going to do this once. If I draw a sample size of 1, there's my sample size of, my sample size of 5 done once, and the mean happened to be 103.600, and you can see where each data value came from here. Right, I'm going to just reset and do what it tells me what I want to do here. Instruction. So the number of samples is 10,000. Okay, so to change the number of samples to 10,000, this is the iterations we're going to do this. Leave the sample size at 5, click on draw samples. Okay, so here's my last one. My last sample I drew, you can see where the points came from right here in the population, and the mean was 84.2. Okay, and then you see right here the distribution of those 5 numbers. But I'm not interested in that. I'm interested in this distribution. So what is true about this distribution? Well, I can still see it's right skewed. Okay, what is the shape of the sample distribution of this mean of 5? Well, it is definitely still right skew. How compared to the other one? Well, notice that before, I mean, you see these, like these these survival times, I can just notice this is definitely extreme. There are outliers. I mean, I'm looking at the middle 50%, and just using the 1.5 IQR method, I can definitely visually, I can see that these are an outlier. Most likely this is an outlier too. I'm not sure how many bad, but maybe even this one could be an outlier. That's how extreme this is. But now notice things are a little tighter. So definitely rice cube, not as bad as before though. Not as bad as population. So it's a little less compared to the population. What is the mean of, so this is, again, this is mean of sampling distribution. Again, what we're saying is each little individual point on that histogram is a sample mean. And this is the sample distribution of those means. And this is the mean of all those means. So when I come over here, it looks like it's 137.265. And the standard deviation is 42.7. What do we learn? Notice again how these two numbers, and these are in days. Again, the unit here is still days. It's an average of 5 days. Okay, so again, we've got to be careful here. This is the standard deviation of those 10,000 numbers. This is the mean of those 10,000 numbers. Each mean consists of measuring 5 days. Okay, so again, we got to be careful here. And this is, again, supposed to be is an approximation to the parameter. Again, notice that these two are nearly the same, yet these two are not the same. So let's turn this around. How are the mean and standard deviation of the population related to the mean and standard deviation of the sampling distribution? In other words, what's the relationship between these two values? One is the mean of the population, one is the mean of the sampling distribution. And what's the relationship between the standard deviation of the population and the standard deviation of the sampling distribution of the mean? I can see that these are almost the same, and this is definitely less than. This standard deviation is less than. It was true the same thing here when we looked at before. Notice that it was the mean here was 4.3 compared to the mean of the population, which was 4.295. The standard deviation of the population was 2.199, and then it brought down to about 0.95. So again, you can see that the standard deviation is going down. And the question we have is, why is that? And does that make sense? And is that what we want? So how are the mean and standard deviation of the population related to the mean and standard deviation of the sampling distribution? So again, please understand that the answer to this question is a key concept in any study. In other words, we're going to mention again that this is the most important lesson. You may need to ask questions. You may need to view this again until you fully understand. This cannot be just an exercise in doing some calculations. All statistics you hear in the news or read in the studies need to ask this fundamental question. If we can answer this question, then the results from gathering data are worthless and meaningless. So what we notice is that the sampling distribution of the mean seems to be equal to the population mean. And is that the case? And the answer is yes. This is true, but it doesn't have to be true. This can only be true if what? Something must happen. This is not automatic. So this is not automatic. So people think, well, it is because it is. No, it's not. It is not just is because it is. It has to be engineered to be true. And this can only be true if the sampling process is unbiased. If this is not true, this is not true. If your sampling process is biased, then these two numbers are not going to be equal. And this is bad news. And why is this bad news? Because that means that your study is worthless. After all, if you instinctively know that if sampling process is biased, then you're not to trust the result. But why would I trust it? Because all of a sudden we have no equality here. Because why do I care about equality? Because the reality is the sampling distribution is the only thing that you actually have a hold of. This is the population, not so much. But the two are connected. So it's the connection between things that we care about. And what do you mean they're connected? Why don't we care about the population? Well, the majority of the time, we will not know the population mean. So we just created a situation where we know exactly what the population mean is and the population mean. So we're doing the simulation so you can see it happening. But the reality is, for most things we care about, the only thing we're going to be able to rely on is a single value. And from that single value, we're about to take this single value, which comes from this distribution. It comes from the sampling distribution. Notice it comes from one of these values, whatever it happens to be. For example, if I click here and click on it, watch, look, I click there, 123. What is the mean of the population of guinea pigs? Well, it's 1.23. If I click somewhere else, no, it could be 189. Oh, it could be 120. So each one of these, 127, 104, 216, 110. So, and then I think, well, that's crazy. I mean, it could be anything. It can not be everything. There's a lot of variability, but notice my sample size is only 5. Keep that in mind. It's all coming together. How are these two related? The standard deviation of my sampling distribution of the mean and the population mean. So we have in this case, population standard deviation and population standard deviation for the sampling distribution of the mean. And the answer is this. They're not equal. But we take the standard deviation of the population we're sampling from, divide that by the square root of n, and you have this. And notice, so as what is true here, and the thing you want to understand is that as n increases, n is my sample size, SD of x bar will decrease. Right? So that makes sense. Why do people say, well, if I had a choice between a small sample and a large sample, I'd rather work with a large sample, meaning the number of values making up your single summary. And it has to do with variability right here. So let's put it to the test. What is standard deviation? 42.872. What is the standard deviation of my population? 96.251. So according to this is not going to be perfect. Again, this is perfect. But again, you would have to reiterate this a million, a million forever. But this is a relationship. We arrive at this mathematically, not by sampling like we're doing. But this course is not going to do that. We're not going to prove this to you. We're just going to prove, or at least demonstrate, that this is definitely a reasonable statement we're making. So if I take now standard deviation is 96.251, divide that again, the square root is going to be 5 because each sample mean consists of 5 numbers. What do we get here? So I get 43.05. This is really the true standard deviation. But this number over here, which is still only from a 10,000 number, is an approximation. And notice, in theory, it should be 43.25. From this iteration of 10,000 is 42.872. Okay, so that's pretty close. In other words, yes, this is what I'm saying. This formula seems reasonable because look, what I did is 10,000 times. My standard deviation is pretty darn close to that number, which says theory says it should be at. The problem is that I only iterate this 10,000 times. I would need to reiterate this like, forever. Out of curiosity, how high can I go? Let me just draw another sample. That's 20,000. Keep going. Draw 30,000, 40, 50,000. The more I go, the closer it'll get, but I may need to go quite far out. Again, unfortunately, this number is not from particular number of iterations. This is from infinite possibilities. Okay, but notice each time I am getting a little closer each time to that number. Almost reiterated this 200,000 times. Look, I'm getting closer to 43. Notice how this number is changing. It's getting closer. I'm now nearing 43. Very slowly, though. And the problem is, we're going to find out, is you would think of, wow, you're adding 10,000 every single time. Yeah, I am, but you think that would be a big difference in getting close, these two numbers to be close to each other. The answer is no, because of the relationship here between these two. The relationship between the standard deviation and the sample size and the old standard deviation. This is non-linear. And we're going to see later, you're going to do this, you're going to create this graph and then see that after a while, even if we kept doing this over and over, we're reaching a point where we're not gaining that much. Well, we're getting closer. That is guaranteed, but it's a slow crawl towards it now.